Hello, everyone. First, I would like to thank Nigar, Ramia, and the rest of the organizers for arranging this needed discussion on creative computer vision. My name is Mohamed Elhoseiny, and I'm assistant professor of computer science at KAUST. And today I would like to discuss with you imagination-inspired AI for art and culture. Before I get started, I'd like to thank all the students who have been part of many of the works that I will be covering today, as well as other collaborators. All of us are aware about supervised learning, unsupervised learning, and semi-supervised learning. In a simple task like classification, in this case, cats, let's say we want to classify between cats and dogs. In supervised learning, we have access to all the labels. In semi-supervised learning, we have access to some labels. In unsupervised learning, we don't have access to any labels at all. In all these forms of machine learning, like techniques, we have access to some form of data. The only difference is whether this data is labeled or not. Today, I'm going to discuss with you how can we augment machine intelligence with imaginary data to facilitate creative computer vision tasks. And I refer to this as imagination-inspired AI or imagination-supervised learning. And I've focused today on topics that relates to art and culture, and mainly cover. I will hop back and forth between creation and also effective expression about artworks with machine learning. So in creation is basically creating like novel art or music. We all may have different definition about what novelty means, and we're going to go through that. And imagining to feel is basically about creating human compatible AI methods that have some awareness about our emotional being, and hence can effectively communicate about the visual stimuli. And I'm going to go through some also work in this direction. So going through the first topic, imagine to create, I would like to discuss with you creative adversarial networks. So work we build on top, like established on top of the popular GAN model by augmenting it with a laws that encourages to produce something new. So the input to the model is a set of training data of existing art styles, including high Renaissance, abstract art, cubism, etc. And the goal is hopefully to produce generations that hopefully not similar to any of existing style norms. This is a joint work. This is work done by Ahmed Al-Gamal, Ming-Shen Lee, myself, and Elhoseiny at the ICCC conference. So the idea was inspired by the principle of least effort, which is can be visualized by this one-dot curve, which you can see that it visualizes in the x-axis novelty and y-axis is hedonic value or likability. And as you may see here, that if novelty is low, people may not like the work, but as novelty increases, people will start to like the work more and more, but not for too long. When the work is too novel to understand, that lack of understanding will lead to lack of appreciation because it lacks connection to concepts that helps us understand what this part means. This is, of course, was mainly a theory in the context of real artworks, but it can be thought that generally it can apply to creative artworks, whether it's generated by art or a machine. And that was an inspiration for us to how on formulating the loss function for the GAN model. Let's start by the GAN model, which is the baseline. If we assume that we feed the WikiArt dataset, which is one of the largest available collection of artworks of more than 80,000 paintings to the GAN model, then we train the data with it, and we may then expect to, let's say, generate the Mona Lisa again. It's a beautiful painting, of course, but it's not a novel content anymore. And this is due that the GAN has no motivation to be creative. And the question comes here, or the question that comes here is how we encourage or motivate the GAN model to be creative. The idea was simple. We started with existing art styles, or we can refer to them also as style norms. This includes the abstract art, cubism, impressionism, high Renaissance, and others. So we tried first to make sure that these style norms are like the model itself is aware about these style norms. And simply what we did is that we added a style classification laws that encourage the discriminator to be more aware about these style norms. So whenever we feed a real painting, we not only like train the discriminator to believe that this is real, we also encourage the model to predict the existing art style. And of course, we train the discriminator to predict fake for generated artworks. For the generator itself, we can see here that it's an unconditional model. It still takes as an input random noise vector, and it doesn't make sense for us to feed the style label because we want to generate actually something different. So we still feed a noise vector, and then we produce an artwork that we still encourage to trick the discriminator to believe that this is real. But at the same time, we want to have a law that encourages these generations to be different or deviate from existing style norms. And the way we do that is by encouraging it to be hard to classify to any of the existing art styles. And we formulate that by high entropy laws. So we encourage pretty much whatever this produce to have an entropic distribution over existing style. For example, if we have pictures like Mona Lisa, this is generated by, let's assume that this is generated by the generator. During training, this will be having a high penalty because this will be a low entropy, and we maximize the goal in our loss functions to maximize entropy. So this generating this image will be heavily penalized. On the other hand, if we have an image like this one, which deviates pretty much from style norms, which are depicted by these 4 piles, but in our training, it's more like the 20 art styles. This produces a high entropy over style norm, and hence the reward in this case will be higher, and hence the loss will be low. So this is some of the a coverage of the one of the art pieces that was generated by CAN model, and you can see also on the right several examples that was generated by the model. Moving forward, a year later, we explored how this sort of loss function with a slight modification on the loss function itself to encourage not only the texture of the visual stimuli, but also the shape. Like in this case, we managed to, in the context of fashion, fashion, of course, is an important domain. It affects our everyday life, and we always seek to get new designs, or to see new designs that might fit our interests. And fashion companies are always interested in creating, pushing the boundaries of their designs in a way that may relate to the company's DNA. So, and in this project led by Othman and in collaboration with Antoine, Yan, and Camille, we explored this topic of creative activity in fashion domain, and we managed to produce some promising results showing the span to extended arm sleeves, which is a shape that did not exist in the dataset. The dataset has pants and t-shirts, and the model somehow managed to produce something that can mix between both of them. Getting back to the other station, like imagination to feel, how can we build AI models that can are more compatible with us, where we can communicate, ask it to communicate about visual stimuli. This can help people, for example, that could be blind to get through artistic experience, or with some help from AI. So with that, I would start with Artemis dataset. It's worked by Banos, Max, Cleese, myself, and Professor Kipis. And in this work, we collected a dataset for effective language for visual art. Some reflections that I found interesting that relates to this topic of understanding emotions, and that there is actually some debates about how emotions are made, and the latest topic towards understanding this was done by Lisa Perry, who is a superstar in this space. And her theory is called the theory of constructed emotion, and she means by that is that emotions are not retrieved by some region in the brain; they are constructed in the moment. And you may see this picture of on the right that may be perceived as a bunch of blobs, but once you get to realize that this is actually a snake, you construct an experience that this can be risky and dangerous, and maybe you may feel scared. However, in the same hand, this same emotional experience, feeling fear, can be joyful in some other situation. Also, it can be enjoyed in some other situations. So if we see a snake or a lion in a jungle, that can be something that we don't want to enjoy for a long time. But if we get to watch some horror movie that we're interested in, we might want to stay watching. And both are different instances of fear experiences, but our behavior towards them could be very different. So the goal of building a dataset that of effective caption is to build AI systems that are compatible with us and more aware about our emotional being, and to also embrace diversity and embrace the diversity and inclusiveness of the diverse emotion that we may have. So, for example, this same painting, someone can feel positive about it, feeling that this reminds him or her of a night sky with stars, and some other person can feel that these dots and colors can make him or her feel uncomfortable or sick. So this is basically the motivation, and this regular caption state factual information about the image, but it may not still go beyond about how these perceived images or perceived object in the image may imply or affect our emotional beings. For example, this is a picture from COCO dataset. It has some description that describe the factual information in the image about the balloons and the clownfish balloons, large kites that are flying in the sky, but it may not capture the emotional aspect of it and of the unsettling balloons. So we collected the data set in this case, and we choose painting because it's a good medium for constructing emotional experience. By design, most of the artistic works are meant to construct emotional experiences. You can see here, in contrast to COCO captions dataset, which is one of the similar computer vision datasets that have advanced the field in many ways. The key difference is the affective aspect. So you can see here both the top row is from Artemis, the bottom row is from COCO. Both of them are images about birds, but look at the differences. In the bottom one, say a small bird that is on the top of a book page, and the top one makes me feel like birds are flying over my head. This is a picture of a bird that gives me hope, and I can imagine myself sitting by the water, listening to the birds. The birds may not even exist here, but the calm, the picture of the calm city helps a person imagine these emotional experiences that may be constructed by going somewhere like that. So here comes the question: how did we collect the data set? And the way we did it, this is by building this user interface, where we first give a participant a painting, and then we ask him or her to pick which emotions is closest to what he or she feels, and we choose Ekman-like emotions labels, and then we give an option to choose something else if none of these emotions were constructed. And then after we pick this, the participant pick this emotion, he then has to explain in no less than 8 words how this constructed emotion, what makes him feel exactly, what explains this selected emotion, what makes him feel this way. So the description is an explanation of why he or she felt that way. So, and we collected a large scale data set of 455,000 like captions, which is a scale that is kind of close to Coho dataset, Coho captions dataset. And that was a distribution over different emotions. You can see that the contentment was pretty high, crossing more than 25%. Amusement, excitement, we have less anger, disgust, fear, sadness, etc. One thing we observed that this work was like first appeared at CVPR last year, and this year we did a second iteration on the Artemis dataset in a paper we call "It's Okay to Not Be Okay: Overcoming Emotional Bias in Effective Image Captioning by Contrasted Data Collection." A work done by Yusuf, Faizan, and Klish. And we observed some weaknesses in the Artemis dataset that relates to the unbalanced distribution between positive experiences, positive emotions, and negative emotions. It seems that people felt more biased towards positive emotions, given that we know that this is an artistic piece. And another thing that we observed is that the descriptions, some of them are very general. Compared these two captions on the same painting, nice looking painting with a bright and nice color scheme. This may be an okay caption, but it's not very specific to the details that you may see in this painting. In the top one, we can see that's a little bit more detailed. The water looks like it has drilled up and made of sailboats. Peach themselves is on the sand, and you can see that there are more detail and refers to particular objects in the painting. And the top one was from the second iteration. And this is the distribution before and after. You can see that it's mostly like there is some bias towards positivity in the old data set. In the new, in the second iteration, you can see that it's almost balanced. So the gains in the data set, we will get soon into how we constructed it. Is that when we train on this in Artemis 2, and it's of similar size or same size as the first version, we found that we gained 20% improvement on the CIDR score. Another thing that we observed that when we evaluated the models, same model trained on Artemis 1 like data and Artemis 2 data, we observed an improvement, like a significant preference by our human evaluators towards the captions generated by Artemis 2. And the only difference is the data source. So this is how it looks like. The way we constructed Artemis 2 by design is to encourage or promote having pairs of paintings that are similar, but construct different emotional experiences. So in each one of these 4 examples, we show an anchor image and a similar image by computing its visual features. and the old annotation versus the new annotation. And you can see here that the new annotations are more detailed and maybe are of an opposite emotional experience. So if the original one is positive, the new one is negative, and vice versa. So so we collected this data to zoom in, just to give you an example. This is a painting. This is the nearest neighbor painting in the data set. This is the old one. The deep blue and purple color gives depth and makes the fruit stand out. Discussed in another. This is an emotional experience described by another participant. The green mold on the rotten fruits on the table is disgusting. So you can see here that we, in some sense, we increase the diversity of the emotional experiences in the data set. In some sense, I want to say that the connection, you may see that the name of our data set is called "It's Okay and to Not Be Okay," and the inspiration for that was actually this like Netflix series about three friends who went through some hard times, and they were helping each other to heal their emotional wounds. You can think of our work as something that tries to embrace the AI or the data perspective. So finally, this is the interface. So we first, what we did is that we picked for every painting that have a dominant emotional experience, meaning most of the emotions are positive or negative, and we have a dominance score that we can refer to the paper for the details. And then we we give participant 24 images that are closest in visual appearance to the given painting, and we ask the person to pick a painting that is similar, which is in the 24 nearest neighbor, but may construct an opposite emotional experience. If for example the given painting is negative, then the person is asked to pick something that is of a negative emotional experiences, and if the given painting is positive, then the person is asked to pick an image that may construct a negative emotional experience. You can see here that by this is also the how the interface look like. You can see that by design, the model, the data collection is promoting similar painting of different emotional experience to exist, and the existence of paintings that are visually similar with contrasting emotional experiences enable machine learning model to be more aware about the subtle differences that might construct two different emotions, like two contrasted emotions, and hence the ability of the model to be more aware of emotions and have less bias towards positive and negative will become better in the new data set versus the old one. And this might explain the improvement of 20% the CVPR score, and also the significant preference of the generated paintings which are, despite that we're using exactly the same model. So this is the interface, and as you may see here, the main we collected 260,000 contrastive examples, and 7,000 or 8,000 of those was no image available. People are given the option that if no image can construct an opposite emotional experiences, they can pick no image, so that we don't introduce another bias. And we combine this data with the original data set to define Artemis 2. Concretely, Artemis 2 training data is same size of Artemis 1, but the way it's defined is that by the contrastive set that we collected, plus 50% of the original Artemis, which is the same distribution. And the evaluation was using the same Artemis C40 evaluation, which is a set of test examples that have 40 captions each, which covers diverse emotional experiences. And hence this we did not define our test experience so that the evaluation is not biased towards the new data. So this is the better emotion gain for what we have. You can see here that the list represented emotions. There are gains in sadness, fear, and even amusement. There are some also additional gains in emotions that were less represented in the original dataset. So this is, in conclusion, what we observe: a 20% gain in salary score and 73% human preference on the models trained on Artemis 2 models compared to Artemis 1. And these are some examples that were generated from models that are trained on the new dataset. So in conclusion, we covered emotional bias, and we collected these dataset to overcome this bias, and we show superior performance compared to the first iteration. Getting to the second aspect, the creation aspect of that we talked about earlier. We also proposed a new model that is appearing at ICCC 2022 later this year, and it's based on a message passing idea. So this model can be integrated on top of any architecture. We built it on top of StyleGAN models. So this shows some examples that were generated by the method, and these are what is in green here is for each painting, the nearest neighbor is showing that the generated painting is quite different from existing ones. You can see here's how different are the generations compared to earlier, like CAN model which is 5 years earlier. So the idea of creative walk adversarial networks, which is the model that we proposed for ICCC 2022, is to model deviation by a random walk class. Let's assume that we have 3 art style classes, C1, C2, C3. This could be abstract art, cubism, etc. We construct a random walk class that starts from each of this existing art style, go for a random walk for T number of steps through the gray points, which are generated art pieces in the current mini batch. And then we encourage the Langdon probability back towards the scene art style classes to be close to uniform, deviating from existing art style norms collectively on the generated artworks in the current mini batch. The key difference is that it's a mini batch level loss versus an example level loss in the case of GAN models. So you can see here we constructed 3 transition probability matrices. Let's say we have 3 classes. This would be 3 times n. N is a number of orange points here, the number of generated images in the current mini batch, and n times n is a transition probability from each generated image to each other generated image for t steps, and then n times 3 is a projection, is a transition probability from each one of these points back to the existing style norms. And so this will construct at the end a 3 by 3 matrix, and I comma j 3 by 3 or k times k in general if you have k art style classes, and the cell I comma j means that what is the probability of starting for a random walk from class I, going through the generated example for t steps, and then land in class J. And what we encourage the landing probability starting from any class to be uniform over all art style classes. So no matter where you start, you should, whenever you go to the creatively generated images, it should be hard for you to go back to and know which class you started from. And we define that as a new deviation loss. And that led to results that outperform a StyleGAN model and a StyleCAN models as well. StyleCAN is basically StyleGAN model plus the original CAN loss in the ICC 2017 paper, which is a baseline. So we compare to StyleGAN 1, StyleCAN 1, and StyleGAN 2, StyleCAN 2. And our models are basically style GAN1 plus the Quan loss and style GAN2 plus Quan loss. And you can see here that our model produce images that are more likable, like have much more rating 4 and 5 ratings compared to other models. Now, the model also is capable of producing artworks that deviates from existing artworks by having larger nearest neighbor distance and higher likability, showing some version of wounded curve that is constructed from this data. So every model is depicted here is visualized by the nearest neighbor from distance from the training data, and the likability score that is collected by human annotators. Something else that we observed is that people, these generated paintings, despite that this is an unconditional model, were able to construct diverse emotional experiences, including contentment, excitement, amusement, disgust, anger, and awe, etc. 13% people felt that this is something not very meaningful. And this is some of the examples that people commented on it. So, for example, the appearance resembles more an exhibition of Egypt in museum. The rouge look of the man and the shirt used are pretty good, etc. We also did study how do we go from an effective description to generate artworks like this example. So use dark colors to make it seem as if ships are going to an enormous place, and it generates a painting like that. This work is done by Clash, and you can see also some additional examples. Interesting to look at all the little details that people are doing, etc. We also extended some technical distribution, the contribution that managed to generate a continuous image from an input text. So in this case, this means that we can generate, given a text description, produce an INR representation of the image, so that we can take XY coordinate and produce an RGB for every location. And this means that you can go outside and generate things outside the boundaries, and you can even generate images of arbitrary aspect ratio. If you apply that on some standard data set like birds, the model can extend the branches and the tail of the bird and other things. And this is based on a paper that's also we did at the CVPR last year, by Ivan Sava, where we proposed an IR-GAN model where the goal is to propose a model that takes Z vector, produces the INR representation, produces a neural network from the Z vector that takes an XY coordinate and produces an RGB for every location. And then we use this INR representation to generate the image of an arbitrary aspect ratio or go beyond the training boundaries. So one last thing I would like to conclude with is we proposed recently this visual GPT model that is appearing at CVPR this year, that aims at data efficient captioning model, data efficient captioning guided by GPT-2. So the idea is, the idea is to introduce a gating mechanism which tries to leverage the language data or distill the knowledge from GPT into this image captioning system that takes as an input the image and produce the caption with a transformer-based architecture. This is getting a mechanism, designing it so that it works effectively is a key idea, and for that we propose this this gating mechanism called SRAU. This gate mechanism are close to zero but not exactly zero. This allows small gradients to disrupt existing ways, and hence we propose this model that sets these weights when it gets close to zero, directly to zero, so that the weights of that comes from the GPT-2 model are not disrupted, and hence the performance. We can distill more clean knowledge from GPT-2 to improve image captioning, where we have only few examples, like few training examples. We found that the model is capable to generate better caption here. A woman and a girl sitting on a table with a birthday party, and other baselines performs like not as well. And the performance on training with 0.5%, 1%, and 0.1% compared to existing baselines was significantly better on COCO, perceptual caption, and also medical report generation data set. So in connection to artworks, one of the things that could be biased in our case is that the culture that we train on is mainly for English-speaking culture. So we might imagine we want similar model to work well on, let's say, Chinese data, on Arabic data, on French data, etc. And in order to do this, we might not have the capacity to collect data. It's of course better to collect as much data as possible, but there is a need to collect to have a better model that can perform effective image captioning in all languages. And since we cannot collect a large amount of data or for all data sets, there's a need to distill knowledge from maybe language models trained on these languages to improve the image captioning performance. And maybe Visual GPT can be one way, or other techniques that can enable image low shot effective captioning can be one way to mitigate this problem. And with that, I'd like to thank you. One of the things that I may point out to as a future work. In this CVPR, we also proposed a new model we call StyleGAN for video generation that is capable of producing like hour-long videos with only 5% more expensive than StyleGAN 2, and on average 50% better than the closest runner-up. To show you how this works, this is, for example, how it generates videos on rainbow, like on jellyfish, and this is how it generates like on faces and sky time lapse. And this might hopefully open the door for maybe enabling longer, like artistic video generation or something like that. Yeah, and with that, I thank you very much.